Okay, my friends. Hopefully you've gotten my email indicating that question 7 on the exam, I accidentally deleted the right answer from the options. So any answer is correct on question 7. I think the testing center has a hard time giving you points for no answer at all. So please fill in one and only one of the possible answers, but any of them will get you points. Do you understand what I'm saying? Don't fill in 2 bubbles, don't fill in 7 bubbles, just fill in 1 bubble. If you fill in 1 bubble, it doesn't matter which one you fill, you will get the 10 points for that question. In contrast, if you fill in no bubbles for that question, you will get no points for that question. You got it? Yes?
What if you fill in a bubble that isn't an answer, like J?
Any answer gets full credit. So if any, but yes, J, yes, the answer to 7 is J. It is also A or B or anyway. All right. So today and the next couple lectures, we are going to hopefully talk about how everything we've learned so far explains the reactions whereby you gain energy from the world around you. Our diet consists mostly of lipids, carbohydrates, and proteins. Those are the 3 main categories, though I suppose when you're eating living things, you're also eating nucleic acids. But we're going to focus on these 3. And we're going to talk about how each of them gets converted into a smaller unit that we can use to generate energy-rich molecules. So, for an example, starch is a polysaccharide that we eat, and we have enzymes that hydrolyze these polysaccharides into monosaccharides, and I'm just drawing one of the anomers of glucose as an example of the kinds of carbohydrates that we that we eat. And you have a metabolic pathway called glycolysis that converts glucose into 2 smaller things called 2 copies of a molecule called pyruvate. And in so doing, you get some ATP out of that process. And then you have another enzyme that catalyzes something called oxidative decarboxylation, and we'll get to that. But that converts pyruvate into acetyl-CoA. And this is an important molecule because acetyl-CoA then gets shunted into something called the citric acid cycle. Unlike glycolysis, which occurs in the cytosol, the citric acid cycle is in the mitochondria. And this process generates an equivalent of ATP. It also releases CO2, and it generates coenzymes NADH and FADH2, which then go to the electron transport chain in mitochondria. That electron transport chain reduces oxygen to water and drives the proton gradient. And that proton gradient, meaning there's more protons outside the mitochondria than inside, is used to drive phosphorylation of ADP to ATP. And that whole process is called oxidative phosphorylation. And then your body uses ATP for all kinds of different things. And we'll talk about some of those functions. But, for moving around to thinking, ATP is involved. All right, what about proteins? Well, proteins, as we've seen, are polymers of amino acids with various side chain groups. I'm just drawing a 2 amino acid section of a protein. But you have enzymes in your GI tract that hydrolyze the amide bonds in proteins to release the individual amino acids. And then these amino acids, like the carbohydrates, get absorbed through the intestinal epithelium and get into the blood and are transported to cells. The fact that, and so you have enzymes in, as I said, in your stomach that do this. You may have heard of trypsin. Trypsin's one of those. And the fact that this happens is one reason why you don't take protein drugs orally. So the most famousest of protein drugs is insulin for diabetes. That's injected. There's active research into other routes of administration, but nothing yet. You don't take an insulin pill, and the reason for that is that as soon as it got into your stomach, proteases would chop it up into its component amino acids, and it would, of course, lose its function, and you would have consumed a nutritious but very expensive protein shake, basically. And it's an active area of research in terms of how to protect proteins from this fate and others. Some of my research is related to things you can do to proteins to protect them from proteolysis. Once you get the component amino acids, your body can take those. I'm going to sneeze, sorry. Excuse me. Do you know my brother-in-law does sneeze impressions? I didn't really knew that was a thing, but he does them pretty accurately. He can do my sneezes. He can do how Amber sneezes. He can do how his late grandpa sneezes, which was a deafening roar. Anyway, so you can take these amino acids and use them to make proteins in your ribosomes. That's where we get our proteins from. But in a pinch, you can also convert the amino acids into acetyl-CoA and use them in the citric acid cycle. So that's a process called amino acid catabolism, and we're not actually going to talk about that in any level of detail in this class. We are going to do glycolysis, oxidative decarboxylation, and the citric acid cycle. Okay, what about lipids? A delicious part of our diet, and the major one that we're going to talk about are these triacylglycerols. First, you have an enzyme called lipase that hydrolyzes the ester linkages and releases the alcohol glycerol, which eventually is shunted over into glycolysis. And then you have these 3 long chain fatty acids. And there's a process called beta oxidation that converts breaks down the fatty acids into individual 2-carbon subunits of acetyl-CoA. So that's the overall picture of what we're going to do. We're going to start with the lipids because this is maybe the simplest and shortest pathway. And then we'll go back to glycolysis and the citric acid cycle. And along the way, we're going to see how the basic reaction types that make this stuff happen are very similar to things that you've seen before. So I'm going to begin with this lipase step, and it's something that you actually saw before and was on exam 1 in terms of mechanism. And the basic idea is ester hydrolysis. I'm showing you what happens here, though, of course, we're not memorizing the catalytic triad, but I want to talk through it just so you can see what actual active site chains are doing. So this is the overall reaction, releasing glycerol and the 3 fatty acids. Here are the 3 key side chains in the enzyme active site. If you actually go look up lipase, you can find the 3 residues, residues in the catalytic triad at these positions. Notice they're not consecutive, so this actually requires quite a bit of of the protein chain folding back on itself. Here we are at residue 152, that's serine. We got to move around up here and then come back to 176, and then we got so much other stuff to do until we get to histidine 263, and then there's other stuff after that. So a complicated arrangement that brings these side chains close to each other. And what they basically do is catalyze the proton transfers that are necessary to hydrolyze the ester. So first, we're going to use the OH group of serine as a nucleophile to attack the carbonyl carbon of the ester. We're basically going to do a nucleophilic acyl substitution reaction. We want to kick off glycerol as the leaving group. But as you learned earlier on this semester, the neutral OH group is not a good enough nucleophile to attack directly and generate a negatively charged intermediate. So we're going to need to remove the proton before it can attack. The thing that removes the proton from the OH group is histidine. But at the same time, a negatively charged aspartate residue attacks and removes a proton from histidine. Okay, so it's sort of a cascade of proton transfers. Now, as you see, aspartate steals a proton from histidine, which then steals a proton from serine, which then attacks the carbonyl carbon to give you a tetrahedral intermediate. Now, pKa's of side chains that you've memorized, if you pay attention to these pKa's, this should sort of make you uncomfortable. How can a base whose conjugate acid has a pKa of 6 remove a proton whose pKa is 16? That ought to be unfavorable by a factor of about 10 billion. And then how can a base whose conjugate acid has a pKa of 4 remove a proton whose pKa is 6? Again, probably not likely. However, there's a couple of explanations for how this works. First, pKa's are measured in aqueous solution for the amino acid on its own. These are in an active site, which is not the same thing as a dilute aqueous solution. The active site is often much more nonpolar than just plain old water, and so that environment can totally change the pKa's. The other thing that helps you out is proximity. These are close to each other, and that can make the resulting interactions between the 2 side chains stronger. And that likely pays for some of the proton transfer energetic cost. All right, so you get this tetrahedral intermediate. Negatively charged oxygen is going to kick off the glycerol alkoxide as a leaving group, and as it leaves, it will pick up a proton from histidine, which will in turn pick up a proton from aspartic acid. And so in the first 2 steps, we've simply shuttled that proton back and forth between aspartate and histidine. And it's actually an open question whether it's actually traded from one to the other or just sort of held in between the 2 and shared. And that would be a pretty strong hydrogen bond that can involve quantum tunneling, and that may provide some of the payment thermodynamically for this other deprotonation step. So we've now got what's called an acyl enzyme intermediate. We've transferred the fatty acid group to an ester with serine. Now we're going to repeat the 2 steps above, only now we're going to use water as the nucleophile. Histidine deprotonates water. The resulting OH minus attacks the carbonyl to get a tetrahedral intermediate, and aspartate deprotonates histidine, and then electrons kick down, the serine side chain leaves, picks up a proton from histidine, which picks up a proton from aspartate, and we've released our fatty acid, and we're back to the starting state of the enzyme. So that's just an example of what enzymes are doing. Sometimes students ask, what the heck is it with this acyl enzyme intermediate? Why don't we just cut straight to the chase and use water as the nucleophile from the beginning? The answer is I don't know. If there were a more efficient way to do it, nature probably would be doing it already. Remember, the purpose of enzymes is to lower the activation energy for reactions that makes the reactions faster. So presumably there's something about this acyl enzyme intermediate that makes ester hydrolysis faster than just direct hydrolysis of the triglyceride. Okay, don't memorize, certainly memorize the side chains and the pKa's. Don't memorize this mechanism. But that's how we get glycerol away from the fatty acid. So let's first talk now about the fate of glycerol. And this is going to give us a chance to talk about a couple of classic reactions in metabolism. All right, so glycerol is ultimately going to get converted to a molecule called Dihydroxyacetone Phosphate. If you look at what we've done, we have to convert this oxygen into a phosphoester. We have to make an ester between this OH group and phosphoric acid, and then we also have to oxidize the secondary alcohol to a ketone. The first step is going to be transfer of a phosphate group from ATP, to the OH group on glycerol to give us this product. The enzyme that does this is called glycerol kinase. Kinases, you'll learn, or if you haven't learned already, are enzymes that transfer phosphate groups using ATP. And then the second reaction is going to involve oxidation of the alcohol to the ketone using NAD+. We'll talk about what the deal is with the proton there, and we're going to talk about both of these steps. The enzyme that catalyzes this reaction is called glycerol phosphate dehydrogenase. And the reason it's called a dehydrogenase is if you look at the glycerol and you compare what is present in the starting material that's not present in the products, you're missing a hydrogen with its electrons and you're missing a proton. And that hydrogen with its electrons ends up in NADH and the proton is there. It ends up being removed by a base. Okay, so we're going to talk about both of these reactions because they're classic reactions, and once you've seen them once, you can understand the mechanism of a ton of other biological reactions. But once we're done, the molecule here is called dihydroxyacetone phosphate. Notice it's got 3 carbons with a ketone in the middle. That's where the acetone part comes from. And this then can jump into glycolysis a few steps in and can ultimately be converted to acetyl-CoA, which then gets oxidized to 2 molecules of CO2, and you release some ATP and some reduced cofactors like NADH. All right, questions so far? Okay, let's talk about phosphate transfer, this step 1. This is really just an example of nucleophilic, well, this is really just an example of an SN2 reaction. We're going to use the third OH group of glycerol as our nucleophile. And we're going to use ATP as our electrophile. So let me draw ATP for you. Oops. Got the three phosphate groups. You have the ribose sugar, and then you've got the adenine base. Okay. And we sometimes label each of the phosphoruses alpha, beta, and gamma. And in this reaction, what I'm highlighting here and circling here in gray and then highlighting in green is going to be a good leaving group. The reason it's a good leaving group is because once it leaves and you have a negative charge on this oxygen, that's the conjugate base of the strong acid. Phosphoric acid has a pKa of around 2, and so this thing can leave and is quite stable. The negative charge is resonance stabilized. So basically, you're set up for a substitution reaction. Another thing I'll point out when it comes to ADP or ATP is that often these oxygens in the phosphate groups are interacting with divalent magnesium, that's the magnesium 2+ cation, which can sort of bind to and neutralize both of those negative charges, and that even enhances the ability of ADP to leave. So what happens in this reaction is we're going to show a base removing a proton from the third OH group of glycerol. And it would be okay if we just did this and then drew the alkoxide intermediate. However, with these enzyme catalyzed reactions, we're going to do something we did before when it came to the imine formation reaction. Recall there that we learned that sometimes proton transfer happens before the rate determining step of a reaction. That's called specific acid or base catalysis, and sometimes it happens during the rate determining step. That's called general acid-base catalysis. Sometimes the distinction between the two is murky. Sometimes it's known in a reaction mechanism, other times it's not. To save ourselves a lot of time drawing intermediates, we're going to actually just show the proton transfer happen at the same time as the negatively charged oxygen then attacks the gamma phosphorus and the leaving group leaves. And that's going to give you your two products, your glycerol 3-phosphate, which I'm going to abbreviate the phosphate group like this, and then it will give you ADP, which I will just draw quickly here. So pay attention to how the negatively charged oxygen is resonance stabilized. I'm just going to write A there for the base. There's our magnesium ion. So this reaction is downhill in energy. Couple of reasons for that. First, the bond that we are breaking here, that's called a phosphoanhydride. And the bond that we made is called a phosphoester. Now, in the same way that a carbon anhydride bond is weaker than a carbon ester bond, we are replacing a weaker phosphoanhydride bond with a stronger phosphoester bond. So replacing a less stable bond with a more stable bond is downhill in energy. Another thing that makes this downhill in energy is the fact that ATP has two extra negative charges on it relative to ADP, and those negative charges would certainly be repelling to the other two negative charges in the ADP backbone. And so removal of this phosphate group relieves some of that electrostatic repulsion, and that's one of the reasons ATP hydrolysis is so favorable. Okay, questions about that? Yeah?
Is the magnesium cation the reason why ATP never goes to AMP?
Is the magnesium counterion the reason ADP doesn't go to AMP? We will see examples of AMP in terms of why ATP is preferred versus ADP for transferring phosphate groups. That the magnesium counterion probably has something to do with it. Also with the fact that it should be more relieving to get rid of these two if your starting material has 4 negative charges than it would be to get rid of the second phosphate group when your starting material has fewer negative charges. I think that may be an explanation. Okay, other questions? All right, let's do the oxidation step. And I'm showing you the mechanisms of these steps because we're going to see similar reactions again and again. So here's your glycerol 3-phosphate. And we want to convert that into a ketone. And the way we're going to do this is with and that's an oxidation reaction. You can tell it's an oxidation reaction because you decrease the number of carbon-hydrogen bonds and increase the number of carbon heteroatom bonds. We're going to do that using the cofactor called NAD+. Now, I believe you've seen NADH before. I think back when we were doing carbonyl reductions with lithium aluminum hydride, I believe I showed you how NADH can do a reduction reaction. Here we're going to do the reverse of that. So NAD+ stands for nicotinamide adenine dinucleotide. It's got a positive charge on this nitrogen. That ring is aromatic, but you could draw a resonance structure in which the nitrogen was neutral, though that resonance structure would put a positive charge on the carbon that is para to the nitrogen. So, and we're not drawing what's down here. Attached to the nitrogen is a ribose ring, a couple of phosphate groups, another ribose ring, and then adenine. I won't require you to memorize the structure of NAD+ or NADH, though you should know how this mechanism works. A base will remove the proton on the secondary alcohol, and electrons will kick down, and you can see sort of where we're going. We would want to be using H- as a leaving group. Of course, that should make you a little sick to your stomach, or maybe a little more than usual in this class. And no giggles, it's okay. I know, it's a terrible, terrible joke. Actually, this class does make you sick to your stomach. So good luck on the exam, sorry. It doesn't leave as H- on its own. In fact, it's handed off directly to NAD+. So H- never gets to experience the full power of having a negative charge. Instead, it's just handed off directly to NAD+, and we'll draw that arrow with these electrons going with the hydrogen to the para-carbon, which is electron poor. Now, we can draw it with the resonance structure on the right, or we can draw it with the resonance structure on the left. We just need a couple more arrows to finish it up. But when we do that, NAD+ gets reduced to the neutral NADH. So we've oxidized a secondary alcohol to a ketone, and at the same time, we've paid for that by reducing NAD plus to NADH. The thing that makes this possible, and likely the equilibrium constant here is close to 1, the people asked during the first class at 9 why losing aromaticity here is possible, because you'd think that would be unfavorable. And the answer is, well, yes, you do. By adding the hydride here, you do lose aromaticity, but you get to go from something that had a positive charge on nitrogen, a pretty electronegative element, to something that is neutral. And so those two offsetting factors make this reduction reaction possible. And then when you couple that to the oxidation reaction overall, you have a reaction that's reasonable. Okay, so this molecule is NADH. Notice that the proton ended up on the base, and the hydride ended up on NADH. And that is why when people write out reactions for reductions, they'll show NAD plus going to NADH and a proton. They don't mean to communicate. Unfortunately, it kind of does communicate, oh, a proton flies off into the abyss. But actually, there's no such thing. The proton is removed by a base. Okay, so those are phosphate transfer to make a phosphoester, and then oxidation using NAD plus. And that's the kind of reactions that we're going to see again and again. That makes dihydroxyacetone phosphate, which we can then, as I said, take to glycolysis. We'll talk about that another time. All right, questions? Yeah?
What does the NAD plus stand for molecule?
Sorry, say that again. What does NAD plus stand for?
Yeah, it's just kind of a random collection of letters right now.
Right, okay. That's fine. Let me... I mean, of course I'll draw it for you, and as you start to dislike what I'm drawing, just remember that you asked. I feel like the cat in the hat. That is not all. Oh no, that is not all. All right, so this portion here is the N portion. This is called nicotinamide. This portion here in pink is the A, that's adenine. And then this linkage between the two, you have two, and it's an unusual linkage, 5' to 5', with two phosphate groups in the middle. That's the dinucleotide. So nicotinamide, adenine, dinucleotide. And then you add the H to indicate that you've reduced it by adding a hydride. But you can see why we don't bother because you can, all of the chemistry happens here. Though, you know, why does nature bother with this stuff? Well, this stuff allows the enzyme to hold on to that cofactor and allows it to get to the right places. Okay, other questions? All right. So now let's talk about the fate of the fatty acid. And we've got two phases. First is fatty acid activation, and then is fatty acid beta oxidation. So our goal in this process is going to be to clip off 2 carbon units at a time from this fatty acid. And to do that, we're actually going to need a leaving group here, and we don't have one. And so we're going to do a reaction that involves ATP. And how to show you this reaction. Actually, maybe, sure, why not? It's going to release something called pyrophosphate, which I'll show you what that is in a little bit. That's going to generate an intermediate that looks like this. And then in the second step, we're going to take that intermediate, and this is called, I forget what this is called. Well, it's called a mixed, dang it, I got that wrong, guys. So take a minute to scribble things out. If you want, you can draw somebody with their eyes rolled in your notes. Here we go again. All right, there we go. Okay, so this converts the oxygen in the fatty acid into basically a good leaving group. And if you're following along at what we've drawn, this is basically AMP. And then in a second step, we're going to take that molecule, we're going to add coenzyme A, and we're going to replace the AMP leaving group with coenzyme A in a thioester. Okay, so let's talk chemically what's going on. I'm going to painfully and painstakingly draw ATP again, though I'm going to skip the adenine part. This reaction is going to proceed differently than what we saw earlier for phosphate transfer. It's a similar reaction. It works for similar reasons, but it has an important difference. And that is that the negatively charged oxygen on the carboxylic acid is going to attack not the gamma phosphorus, but instead the alpha phosphorus. That's going to be guided by the enzyme, but the reason it can do that is because what leaves is also a good leaving group. This leaving group, once it's left, is going to be called pyrophosphate, and the biologists and biochemists abbreviate that as PPI, the I for inorganic because it no longer has carbons on it. This is basically an SN2 reaction, and the bond we make is between the oxygen of the carboxylic acid and the phosphorus, the alpha phosphorus of AMP. So that's the bond that we made. And this reaction sort of has a secret weapon because the pyrophosphate group that leaves, and I didn't draw the magnesium counter ion there, you can assume it's there. The pyrophosphate group that leaves has an embedded thermodynamically favorable reaction it can do, where water can hydrolyze the pyrophosphate, which has a phosphoanhydride linkage, into 2 phosphate groups. These are often individually called inorganic phosphate groups, and that is very downhill in energy. So one thing that helps this reaction happen is not only, well, I'm replacing, if you look at the bond I'm breaking there, that's a phosphoanhydride bond. Whereas the bond that I made is more of a mixed anhydride bond. It's sort of a half carbon, half phosphorus anhydride. So in terms of bond stability, it ought to be basically the same on this side of the equation versus that side of the equation. We're replacing a fairly weak bond with another fairly weak bond, but the thing that drives this forward is once the pyrophosphate group left, it gets hydrolyzed, and that's downhill in energy. Okay? This is an example, I think, of a coupled reaction. Sometimes you can use a very thermodynamically favorable reaction to drive a slightly less favorable reaction forward. Okay, questions about that? Yes?
Why doesn't the last phosphate leave as well? Is that just because of the enzymes?
Why doesn't the last phosphate leave as well?
Like all three of them instead of two?
All three of them instead of two. Well, let's see. To do that, you would be proposing that this oxygen attacked here to make, I think, an ester with the sugar. And I suppose that would be okay. I don't know whether that happens or not, though that would be just a regular ester, which isn't very reactive. So there's a reason why nature wants this to be a phosphate group here, and that's because in the next step we want to use that as a leaving group. Okay, what else? All right, so next is basically a nucleophilic substitution reaction. I'm not going to redraw the AMP group, but understand that it leaves as AMP with a negative charge on that oxygen. So the way this happens is this is basically just nucleophilic acyl substitution. You're going to see a nucleophile attack the carbonyl carbon. A base probably has to remove the proton. This CoSH is the coenzyme A thiol. It has a sulfur at the end of it that's a thiol sulfur. You can remove the proton and at the same time attack the carbonyl carbon. That gets you a tetrahedral intermediate that looks like this. And then electrons kick down and kick off the leaving group, which is AMP, and you end up with this thioester. The reason you want a thioester versus just the AMP mixed anhydride is that the thioester should be more stable than the mixed anhydride, but it is still pretty reactive. So it'll last, I think, longer. And moreover, what we want to get out of fatty acid metabolism is individual units of acetyl-CoA, which you can think about as being sort of embedded in this fatty acid. If we could only somehow clip off those two carbons, we would have acetyl-CoA. And so the next few steps are a process called beta oxidation. And the beauty of this process is it just makes chemical sense based on reactions that you know. So here is the thioester, here is an alpha carbon, and here is a beta carbon. Now, if I wanted to clip off acetyl-CoA so that I could use it in the citric acid cycle, that would mean that my goal is to break a bond between alpha and beta carbons. Okay? Now, right away, you should be thinking, when have I broken a bond between alpha and beta carbons of a carbonyl compound? You should be thinking retroaldol or retroclaisen reaction. But the problem is that we're not set up for that because both the aldol and the Claisen reactions will have oxygens on the beta carbon. We don't have that here. And so we're not yet ready to break that bond, but we're going to get oxygens there, and that is why this is called beta oxidation. Okay? So step one of this process is going to be to convert the fatty acid into the corresponding alpha-beta unsaturated carbonyl compound. Notice that doing this is going to require us to remove a proton and a hydride. So this is going to be an oxidation reaction. And instead of using NADH, for reasons I don't understand, nature will use a different oxidizing agent, and that's called FAD. And I'll show you the business end of the FAD molecule in a little bit. The mechanism likely proceeds as follows. A base removes the alpha proton. That's easier to do than for a regular ester because thioesters are more reactive than regular esters. That means they're better at nucleophilic substitution and they're better at making enolates. So step one is you make the corresponding enolate. I'm going to draw, let's see, here's the beta carbon still, here's the alpha carbon. So the base removes the proton, and the base is from the enzyme, so that's where our proton goes. We now have an enolate, negatively charged carbon on the alpha carbon. Oops. Now we're going to want the negatively charged carbon of the enolate to kick down and kick off hydride as a leaving group, except we know that hydride is a terrible, horrible, no good, very bad leaving group. So we're going to use a different reagent or a different molecule to receive that hydride. We're actually not going to talk a lot about why this reagent works. It's another, get the structure wrong probably. It's another example of a hydride accepting reagent. One, if you look at the structure, and this is actually attached to a ribose sugar, it's a very much similar in structure to NAD+, only it's the different group up here. This group is derived from riboflavin in your diet. This nitrogen here, the sort of para position, is electron poor, and you can see that it's conjugated to these electron withdrawing oxygen groups that make that nitrogen electron poor. So instead of leaving as a hydride, that hydride gets delivered directly to that nitrogen. And then electrons kick down here, and then we pick up a proton from some source on this ring nitrogen down there. We'll just pretend it's the conjugate base of or the conjugate acid of our base. But the effect is that we now have a double bond between alpha and beta carbons, okay? And we have reduced FAD to FADH2. All right. So here's your proton. There's your hydride. Now, that should seem like progress to you because alpha-beta unsaturated carbonyl compounds are aldol products. So we're already getting towards something where we could consider breaking the bond between alpha and beta carbons. We will continue with that next time. In the meantime, good luck on the exam.